All right, so for the last talk of SNARK Week, I'm excited to introduce Quang, who's a PhD student at Carnegie Mellon and our intern for the summer here at A16Z. So he's already produced many strong results in both theoretical and applied cryptography. And today he's going to tell us about the security properties of SNARKs that you really want when you deploy them in actual applications and how to show that they have those security properties.
I'm very honored to be talking here today at the end of SNARK Week, which has been very exciting for me personally, and I hope for you as well. So my talk is going to be sort of a survey or overview of the recent advanced security results for SNARKs. Basically, what sort of security notions that SNARKs should satisfy when they're deployed in practice and when they might encounter attacks that may not have been analyzed very much in the theoretical literature. We all know and love SNARKs. They're succinct, non-interactive arguments of knowledge. And basically what they are is just they are a certificate or a proof that is both short and non-interactive. So the prover does not need to do any sort of interaction with the verifier, just sends over a proof. This proof is also very fast to verify. And in terms of standard security notions for SNARKs, you want two of them, right? The first one is that if the verifier accepts a proof, then it means that the prover must have known some associated witness W to the statement X. And the second property is zero knowledge, which says that the proof itself, it can be simulated without knowing the witness. And these two security properties are proved basically with every SNARK constructions. If and I think knowledge soundness is a must, and zero knowledge depending on the SNARK whether you want it or not. Okay. And SNARKs have found so many applications both in the blockchain space and beyond. In the blockchain space, we have all these zk rollups and the promise for these private smart contracts or private transactions. I'm sure A16Z has a lot of working with a lot of portfolio companies on all of these exciting applications. But beyond blockchains, there are also many other interesting applications, such as image attestation. So if you see an image on the New York Times, right, how do you make sure that it has come from a reputable source? And this whole process may involve a lot of transformations from the original image, which is very high quality. And so what you can do is you can just do a SNARK of these transformations, that these transformations have been applied correctly to get the final output. Similarly, you can also do a SNARK proof of correct AI training or correct AI inference. Or you can show that, do a SNARK proof to show that your account is not on some given block list on some federated website, and many, many other applications. So with all of these deployments here, I guess a very important question to ask is that, are these security notions that are usually proved for SNARKs, are they enough to guarantee security when SNARKs are deployed? It turns out that in many applications in practice, these security properties are not enough. And roughly the reason why is that, for example, if you look at knowledge soundness, it's defined in this standalone setting. You have one malicious prover that is outputting a proof. But in actuality, this malicious prover may see many other proofs from different parties. Okay? And in this context where SNARKs are deployed, we also want to guarantee security when it is composed with other protocols as well. With these extra proofs that a malicious prover might have, there may be a very real extra attack vector here, which is called a malleability attack. What this attack does is that a malicious prover may see a proof and then modify that proof to be some other different proof without necessarily knowing the underlying witness at all. Malleability attacks have actually been sort of devastating in practice. Maybe not for SNARKs, but for signature schemes. So I think allegedly what happened with the Mt. Gox attack is that the Bitcoin signatures for Bitcoins at the time were malleable. So what could happen is that somebody submits a valid batch of transactions, Bitcoin transactions, with some signatures. Then because the signature is malleable, someone else, some adversary, can take that signature, mull it to be different, and then submit that first. You front run the actual valid transaction batch. And if that can happen, then it is a valid malleability attack, and you may get all the rewards for that transaction batch. Sort of a very simplified scenario for what could go wrong if your SNARK or your signature scheme is malleable. We really want to rule out these malleability attacks in practice. And one such strong notion called simulation-extractability will help rule out this attack. This is basically adapting knowledge soundness to this more general setting where a malicious prover may see arbitrary proofs of his choice. So let's say here the SNARK is zero knowledge. There's some simulator that can simulate any proof that you want. And you give this Oracle access to the simulator for the malicious prover. And you still want knowledge soundness to hold, which means that whenever the malicious prover outputs a new proof, if this one is not something trivial, like it has been queried before, then it must know an associated witness to this new proof. You cannot generate new proofs out of nowhere. This means that you can now forget about malleability attacks, because every new proof that anyone produces will come with an associated witness, even when you can see all the other proofs. It's also very helpful for many applications. So for instance, in a blockchain setting, you want your transactions to be non-malleable, right? And one way to do that directly is if you prove the whole transactions with a single SNARK. And that SNARK is non-malleable or is simulation extractable, then you're good. If it is not, then there are ways to make it so that, compose it with other primitives such as just ordinary signatures, so that the final scheme is non-malleable, but that sort of adds extra overhead. So it's very helpful if your underlying SNARK is already proven to be simulation extractable, because then it can just be used directly for these applications. So these are the benefits of proving that SNARKs are simulation extractable. And the question now is, are existing SNARKs satisfy this strong property?
Question?
Yeah.
So was that definition in the context of SNARKs in the upper left, or they were thinking of something else? Or?
Yeah, it's in the context of just proof systems in general. Yeah. It predates the introduction of SNARKs, just when they had proof systems or non-interactive proof systems. So let me give you sort of a very quick overview of where we are in the context of simulation extractability. At the moment, there are many popular zkSNARKs that have been proven to be simulation extractable. This list includes, say, Gross16, Bulletproof, Plonk, Marlin, SNARKs, and Spartan, and so on, with the exception here that Gross16, it satisfies this somewhat weaker notion of simulation extractable, where given a proof, you can re-randomize that proof. But up to that, you cannot do anything else. Some of these SNARKs satisfy a stronger notion known as UC security. UC here stands for universal composability. So I'll talk more on this later. It's sort of a stronger properties that also guarantees security when composed with arbitrary other protocols. And there are now established templates for proving simulation extractability for SNARKs. It basically boils down to the standard security properties, so knowledge soundness and zero knowledge, plus a very mild property called weak unique response. And I'll get to that later. It basically says that given a SNARK proof, you cannot continue it in a different way at any point during the SNARK proof. On the downside, it turns out that many SNARKs that are deployed in practice, they lack a proof of simulation extractability. It's either because, well, the full specification of that SNARK has not been really written down and analyzed anywhere. It may contain optimizations compared to some original protocols, like this is what happens with many Plonk variants, and so on. And also, despite having a template, sort of instantiating this template still require some case-by-case analysis. There is no simpler properties that you can show that immediately implies a weak unit response, which then immediately implies simulation extractability. So I'll also get to this when we go to the details. So let me go into the details for simulation extractability, and then also talk about usage security and end with some open questions. The central point in proving simulation extractability is that, well, it's mostly just knowledge soundness, right? Except that the adversary has a bit more power. It has the power to access some additional proofs of its choice. It would be most natural to reduce it to just knowledge soundness. Well, that is basically what is happening, is that it would be very nice if somehow we can just ignore all the extra proofs that it sees and says that these extra proofs, they do not help the adversary in any way towards crafting a new proof. And that's basically exactly how these simulation extractable results are proven. You just show that either this final proof that the adversary produces has no overlap with prior proofs, or if it has any overlap at all, then it must be identical to a prior proof, in which case the output is trivial. And so we're going to instantiate this template for different kind of SNARKs. And in fact,
Question?
Yeah.
What does overlap mean in this context?
Right. So usually a proof, you have like, it consists of some components, right? And overlap here means that some components are the same, but other components are different. It sort of makes more sense when I get to exactly what those components are.
Okay. And then I guess the other question would be, so what exactly is the model? So like as a prover, I give you like, you try to generate pi and you get to query whatever, you get to generate as many x prime primes you want for x prime not equal to x. Is that how I should think about it?
Yeah, yeah. You have this simulation oracle. You ask it whatever statement you want, even possibly false statements, and you still get back simulated proofs for all of them. And so you can just get all these proofs. But then whenever you produce a new proof, it must be the case that you produce that proof in an honest way somehow. Like you actually use a witness for that proof.
Or should we be thinking of the simulated proofs as coming from the simulator whose existence is guaranteed by the zk property, or just from elsewhere in the protocol, or all of the above?
Yeah. So this really only makes sense for zero knowledge SNARKs. So this is actually the zero knowledge simulator. Okay. Yeah. I'll get to in a moment, like at the end, like what happens if there is no zero knowledge. Mm-hmm. And I think it's still sort of an open question to just show non-malleability for SNARKs are not zero knowledge.
Mm-hmm. Because the Mt. Gox attack was a malleability thing where there was no simulator or anything. It was just adversaries were seeing proofs and mulling, well, signatures and mulling the signatures, right? So
yeah. But the signatures is like built from a zero knowledge identification protocol. Yeah.
So in your application, you motivated with that the adversary sees other proofs and should not be able to come up with the new proof. But here you are giving a simulation oracle. Why not giving an actual proof oracle, which takes a statement? Probably the oracle is unbounded, computes the witness, and computes an actual proof. Why not give an actual oracle and instead give a simulation oracle?
Yeah. I mean, one way is to sort of strengthen the definition. So now you can also see valid proofs for false statements. Another is just simplicity. So if you need to, like, say, you need to model like the adversary can see proof for statements of its choice, right? So what does it mean for adversary to specify a statement without any possible witness? Then like how is the proof generated?
I'm slightly confused, maybe. Like, according to Justin's questions in your answer, the proof simulation oracle is the same simulator as for the zk from the zk property.
Yes.
But that simulator can be run by the verifier even without knowing the witness, right? Like so in particular, the prover could run this simulator even before I even gave him access to this model. Does that question make sense?
Yeah, that question makes sense. So what I'm sweeping under the rug here is that the simulator has some extra power over the honest parties, or even over the adversary. Right? So like if you have a proof in the random oracle model, then the simulator can reprogram the random oracle queries.
Also, don't the simulators sometimes run in it's like expected polynomial time, right? So sometimes you can, in this model, you can just ask it and you don't like think about that. But like if you're sitting there running your simulator, you can run to a situation where you're like, oh, I'm running forever. Like
Yeah. Simulator has some extra power, like reprogram random oracles, run in expected poly time, or have some trapdoor that allows for simulation. So this is basically the template. And instantiating this template is a little different for sort of two separate kind of SNARKs. So this is a very broad attempt to classify all SNARKs, at least with respect to how simulation extractability is proved. So on the one hand, you have SNARKs like Gross16, which are based on this linear PCPs. And basically, you have some very long CRS. The prover, knowing the witness, will take some elements from the CRS and then craft a proof consists of some group elements. Whereas in the Fiat-Shamir-based SNARKs, what happens is now the two parties actually use a random oracles and then try to, you have, originally there is some interactive protocols with the verified challenges being all random. And then you collapse this into a non-interactive proof by letting the challenges, these CIs, they're derived via some hash function, which we model as a random oracle. Okay. So very roughly, these two camps of SNARK design. And I'm only going to focus on the second camp, which actually is sort of how most SNARKs nowadays are produced. For the first camp, I'm just going to say that simulation extractability, you reason within this algebraic group model or generic group models. And within that reasoning, you also are going to show that if you have a new proof, then it cannot have overlap with any of the prior proofs, and so on. But the reasoning is somewhat different, so I'm going to skip it. Before I show you how to prove it, let's show an example where it is not the case. Let's say you take some Fiat-Shamir non-interactive arguments. Let's say this guy just has like 2 message and 1 challenge. And then you're going to somehow double this protocol. You double it by just proving for this product relations where you have 2 different statements and 2 different witnesses. You layer the 2 executions sequentially. OK, so I claim that this protocol right here is not simulation extractable. In fact, it's very malleable, and here's the malleability attack. The idea is that because you have these 2 protocols that are layered sequentially, what you can do is you can have a mix and match attack. Right? You get, let's say, this malicious prover is going to need to declare 2 statements, right? One of the statements is not going to know the witness. The other one, it will know the witness. So then it can ask for just some arbitrary proof of those 2 statements. And it's going to keep the first part, like keep the first execution, but it's going to change the second execution. So when you change the second execution, it can do so because it knows the witness to the second statement, this W prime to X prime. And because of that, it can generate the second part of the proof here in an honest manner and keeping the first part. Okay? So because of this mix and match attack, you basically have a new proof, that is this AZ, A star, Z star, where this AZ is part of a prior simulated proof. So if the statement X here is somehow a false statement, then the adversary has won this malleability game, right? So what we want in these Fiat-Shamir non-interactive proofs is that the protocols should not be able to be broken down like this. Or in other words, you do not want parts of the proof to be reused later on. So there is a property that somehow captures this intuition that you should not be able to modify part of the proof and continue from there. Okay, so this property is called weak unique response. So let's dive into what this property is. Okay, so it's defined by this game. First, your malicious prover is going to choose any statement at once, and then it gets back a simulated proof. Now it's going to try to produce a different proof pi prime such that these two proofs, they differ, but they agree on at least some of the components. Right? The components here just means the individual messages, A1, A2, and so on. So they agree up to some point, but then they diverge. The prover is going to win if it manages to do this. Okay, so takes in some proof and then produce another proof where there's a branching up to some components or some rounds. And the claim is that if it is impossible for a malicious prover to do this kind of attack, then it is also impossible for the prover to carry out a malleability attack. The idea is basically now simulation extractability is going to be proven as these two standard security properties, knowledge soundness and zero knowledge, plus this weak unique response property. Let me recall you what the simulation extractability game is again. So you have this malicious prover, right? It's going to have access to arbitrary proofs of its choice. And you're going to want knowledge soundness to hold. And what it means is that there is some extractor that is going to extract out a witness for whatever proof that the malicious prover outputs. And now the malicious prover is going to win if this proof is accepting, but somehow the witness is not a corresponding witness, and also that the proof is not a trivial proof that has been queried before. So this is the original game. Now we're going to do sort of a hybrid into a different game where you want to rule out the chance of a prover using a weak unique response attack. So now you're going to additionally reject if this pi star has any overlap with a prior pi, with a prior proof that has been queried. Basically, this is the same condition as in the weak unique response game. And so the claim here, which is somewhat easy to prove, is that if somehow in game 2 you abort, then it means that the weak unique response condition is achieved by this adversary. And therefore, you can break weak unique response, right? Which shouldn't be possible. And then in game 2, now that this new proof has no overlap with prior proofs, what you can do now is you can directly reduce this SimX adversary to a knowledge soundness adversary. And so you also win, because knowledge soundness is supposed to hold with respect to this proof system. So basically, with these two claims, you can now see that simulation extractability is just normal security plus weak unique response. So how is weak unique response actually proved for various different protocols?
Sorry, could you talk more about the proof of claim too? Because like in the knowledge soundness game, there will be no oracle. So like how do you do the reduction?
Yeah, so the reduction is you basically have this adversary. It's going to just run a simulator on its own and interact with this P star. And the reason why this simulation on its own still works is that this output proofs here have no overlap with prior proofs, and therefore the simulation goes through.
I see. So you're saying like there exists some simulator algorithm that this reduction can run.
Yeah, it can run.
Okay.
Like it can run some sort of local simulator algorithm. It's not supposed to be, like in general, it's not supposed to be exactly equal to the, I guess like global simulator. But with this particular property that this new proof has no overlap, then the two simulations are the same. Let's go into a simple protocol. Right? Let's go into this SNARK protocol, which is used to prove the knowledge of the discrete log of some group elements. So here you have some group element big X in some prime order groups, and you want to prove the knowledge of its discrete logarithm with respect to this base G. Let me also just recall the protocol very quickly. Basically, it consists of the first message being just a random group element, right? The verifier is going to send a challenge, which in the non-interactive case is derived with the random oracle. And then the prover is going to send a response, which sort of like incorporates both the discrete log and the first message. And then it's going to have some verification property that the verifier is going to check. So with this protocol in mind here, we want to show that the response is unique, right? The response here is just this second message G. And if you look at the verification equation, it follows that if everything else remains the same, so if A is the same, if X is the same, and G is the same, then there's only one value of Z that is possible, right? So in this case, the unique response just holds with probability 1. And then we derived this prior results back in 2012 that SNARK is simulation extractable. But now let's try to go into more complicated protocols. And in fact, this polynomial IOPs, or interactive oracle proofs, this is sort of the backbone of modern SNARK constructions. Okay. And let's see how weak unique response can be proved for such general protocols. Again, let me recall just very quickly how these protocols work. It comes from some information theoretic interactive protocols, where in each round, the prover will send oracles to some polynomials, and the verifier is going to respond with some challenges. After all this interaction is done, the verifier can now sample some query points. There is some sort of indexing here that is maybe a little bit hard to see. I just wanted to convey the general ideas that it may happen in multiple rounds, and in each round there may be multiple polynomials. The verifier is going to sample some query points. It's going to query these oracles to get the evaluations at these points. And then it's going to decide based on these evaluations. This is an interactive protocols. You're going to collapse this into a non-interactive proof by essentially instantiating these polynomial oracles with polynomial commitment schemes. So now you're going to send commitments to each of these polynomials. And you're also going to send, in turn with the evaluations, also an evaluation proof, these pi evals. Okay? So that's what a polynomial commitment scheme does. And then you're also going to apply Fiat-Shamir to this protocol to make it non-interactive. So with these SNARKs that are derived from polynomial IOPs in this way, how are we going to show that weak unique response holds for the final SNARK? A prior work has shown that this weak unique response property, it would follow from basically two conditions. The first is that the polynomial IOP queries, they're unpredictable. So for instance, if the queries are just like some of these challenges, then they are going to be unpredictable because the challenges are random. And secondly, you want the polynomial commitment schemes to have weak unique proofs of evaluations. So I'm not going to too much details on these weak unique proofs. It basically just says that for a fixed commitments evaluation point and evaluation, there is at most one proof that it can produce to show that this evaluation is correct. And also with some other standard properties of these PLP or PCOM. Right. And the proof idea here is basically you look at this proof here, which consists of the commitments, the evaluations, and the evaluation proof. And you look at, you consider when the two proofs first diverge, right? If we're doing the weak unique response, you need to have two proofs that diverge at some point. So if it's going to diverge at one of these evaluation proofs, then it means that the protocol does not have unique proof. If it diverges at one of the evaluations, then it means that it breaks evaluation binding and so on. Like if it diverges at one of the polynomial commitments, then you basically can't do it because the queries are now unpredictable. So you don't know how to derive the evaluations. That's the end of it for simulation extractability. This is a template that basically you can use this template to show that the existing SNARKs that come from polynomial IOPs are simulation extractable.
Is there a relationship between weak unique response and like round by round soundness or notions that just come up when analyzing security of Fiat-Shamir and sort of the standard knowledge soundness setting?
Yeah, I don't know, but if there is, that would be very nice.
I mean, it's interesting that like your canonical example of something that is not simulation extractable when using Fiat-Shamir involves repetition, which is the canonical example of when Fiat-Shamir is just not secure, period.
Yeah.
And they feel a little bit related. Okay.
Yeah.
Yeah, and also the weak unique response seems similar, right? Because you have like up to a certain point the string's the same, then you kind of diverge to get an accepted proof, and that's like exactly what round by round soundness tries to say you can't do, right? So it would be interesting to see if there's a relation there.
Yeah, definitely. So let's talk about UC security. So what is UC security anyway? And it basically tries to solve the following potential problems. Okay? So when SNARKs are deployed in the real world, they're usually deployed alongside many other protocols, right? And in this case, it's not enough to just show security with regards to knowing many other proofs. You also have to show security when you can see sort of the transcript of many other protocols that are executing alongside it. So you need a very nice like theoretical model that can capture composability with respect to arbitrary protocols. And this is exactly the goal that the UC framework is designed to do. So it's introduced by Ran Canetti back in the 2000s, and now it has become sort of a gold standard for cryptographic security, because if a scheme is proven UC secure, then it can be composed arbitrarily with other protocols in this framework and still remain secure. UC security, in a nutshell, it says that a protocol is secure if it behaves like some ideal functionality. And in the particular case of non-interactive proofs, it is this ideal functionality. I call it FNISC. NISC just means non-interactive zero knowledge. This functionality can take in two kinds of queries, right? One is the proof query, and one is the verify query. When you send in a proof query, you're going to send in the statement and the witness, and you're going to get back a proof. And then later on, you can get that proof and send in a verify query, and it's going to give you either accept or reject. And moreover, this ideal functionality, it should behave like the simplest version of a proof system that you can imagine. So it's going to look something like this. You want the proof and the verify algorithm to be as simple as possible. So what is the simplest thing that you can do? Well, when you prove something, you just sort of assign this statement and witness pair to some string, right? The string is the proof, and you give it back the string. You're going to store this. There's some sort of database where it remembers all of the proof that it has been given to, that has given. And then when someone tries to verify a proof, it's just going to look at this table. For every proof, it's going to extract out some witness. It's going to check if this witness is valid or not. And if it's valid, it returns accept. If not, it rejects. Yes?
This may not really matter conceptually, but why does it have to store a table rather than like signing or encrypting the witness or something so that when it gets it back, like you could imagine a version of this ideal functionality without a bunch of storage.
What do you mean by encrypting?
Well, like you said, it like stores the witness in a table and looks it up later.
Yeah.
It could just like encrypt the witness and give that out as a proof.
So you want the proof to, it's the succinctness, right? You want the proof to be actually comparable to the proof of an actual protocol. And if it's a SNARK, then you want the proof to be succinct. So the ideal functionality is sort of doing all the work here. It's some trusted third party that has this stateful implementation.
Somehow it's conceptually weird though that the ideal functionality is stateful where like a proof system is not stateful, right?
Yeah, but I guess that's the nice thing, that if you can prove UC security, then somehow a stateless thing is as powerful as a stateful thing. And also let me just show you what UC security actually means with respect to this ideal functionality. So in an actual protocol pi there, in the real world, is going to be UC secure, it's going to UC realize the functionality FNISIC in the ideal world if for every adversary, it can interact arbitrarily with the protocol pi and also with some ambient environment. Right? The environment here, you can think of it as a distinguisher. It's trying to determine whether it lives in the real world or the ideal world. So interacts with everything, interacts with the protocol, interacts with the adversary, and it tries to figure out whether it's in the real world or ideal world. And if it cannot figure that out, then it means that this protocol is emulating the ideal functionality. In the ideal world, you need to replace the real adversary with some simulated algorithm that you're going to define that somehow sort of manages to make it hard to distinguish whether you're in the real or ideal world. Okay. And then maybe UC has had a lot of extensions to handle like global functionalities or adaptive corruptions and so on that I'm just going to sweep under the rug for this talk.
Sorry, this might be a basic question, but in your diagram below, zero knowledge intuitively, I can see that the verifier only learns the bit, so it's zero knowledge in some sense. But what's the intuition for knowledge soundness in this diagram?
Yeah, so it's in the implementation of the ideal functionality. So given every proof, you have some extract algorithm that's going to spit out a witness.
Oh, and rewinding is not a thing here?
No, it's not. Yeah, so that's actually the next slide. So I want to convince you why achieving UC security is difficult. And in particular, you've seen this other simulation-extractability property, right? Does it immediately imply UC security? And the answer is not always. The reason is that you have this extraction and simulation in the UC framework. It has to be straight line. Whereas extraction in many of current SNARKs, they rely on rewinding the adversary, and hence they're not straight lines. And the same for simulation. There may be something the simulator does that is just not allowed in the UC framework. Because of this, there have been prior attempts at trying to overcome these limitations and hence to achieve UC security. One such attempt is to encrypt the witness and send it together with the proof. Right? So now extraction becomes simple because the extractor can just hold the secret key and then decrypt the encrypted witness. But then this loses succinctness, and we want succinctness in a lot of applications. Secondly, what you can do is use this so-called Fischling transform, which is a straight line version of Fiat-Shamir. Fiat-Shamir, usually you you can only establish security through rewinding. But with Fishlin, you can actually get a straight line proof, straight line extraction. But the cost to that is that you have an overhead in the proof size and in the proving time. Yeah.
There are a lot of straight line extractors for SNARKs, that use fiat Shamir. If you can watch the random oracle queries.
Yes.
So what's the issue with those? Is it that you?
There's no issue with those. It's going to be on the next slide.
Oh, okay. Okay.
But like some other protocols, let's say like bulletproofs with groups, then I think the only known way is either you use the object-provided group model or you need to use rewinding.
Right. Okay. So if you establish that a SNARK is simulation extractable and it has a straight line extractor in the random oracle model, is it automatically UC secure? I mean, you do need programming the random oracle for zk. Is that an issue?
Yeah, that can be fixed with like adding a random salt to each of the rounds. But yeah, I think it should work, but no one has written down, a proof of this. So maybe it's still a good idea to write it down somehow.
Okay.
Yeah.
Like it seems like it should work, but it's a pain to write down.
Yeah. So what is really interesting to us is can we actually get UC secure SNARKs without any overheads? And two recent works show that indeed for certain classes of SNARKs, you can have UC security without any overhead. Like literally the original construction is already UC secure. So the first one are these so-called hash-based SNARKs, where you can observe all the random oracle queries and extract from that. So now extraction is straight line, and a recent work by Chiesa and Giacomo Fenzi, they showed that this transformation for any hash-based SNARKs that satisfy these two soundness and zero knowledge notions will be UC secure. A second work showed that in the global generic group model, so basically everyone gets access to some generic group and can only do group operations through queries to these generic groups, then the gross 16 SNARK is also UC secure. Here, you also need to modify the ideal functionality a bit to make sure that you allow re-randomization of proofs, but other than that, it's UC secure. Okay, and the main idea that I just discussed is that now you can make extraction and simulation to be straight lines, and hence the proof sort of goes through.
So like in breakdown, if you use an error correcting code without efficient decoding, the extractor is no longer known to be straight line. And would your guess be it's still UC secure, it's just we don't know how to show it?
Yeah, I don't have a good intuition on that.
Okay.
Yeah.
Are there? I mean, does it generally feel like all SNARKs people use have all these strong security properties we want them to, and it's just a pain to prove it? Is that's generally your sense, or yeah?
I don't think so. Maybe with these global generic groups, maybe you can show that a lot of group-based SNARKs or pairing-based SNARKs are actually straight line extractable and therefore maybe UC secure. But yeah, I guess it's just a lot of overhead in all the definitions, and nobody has done that yet. These two results are very recent. They're in the last month.
But we don't know any non-trivial, interesting attacks on the UC security of SNARKs people are using today.
Yeah, we don't.
Okay.
So there are other definitions of soundness, I don't remember the names, but sometimes you give the advice string to the adversary. So I was wondering if there's any results on how the UC security in terms of a security definition compares to those definitions of soundness. Does that make sense?
Yeah. So soundness with auxiliary inputs.
Yes.
Okay. I can't remember off the top of my head, but there might be. Yeah, we can talk about this offline. So that's both simulation extractability and UC security. Let me end with, say, 2 open questions that I think is very valuable to answer. The first is that we've mostly talked about SNARKs, but recently there's also been a lot of work on more than just SNARKs, and in particular these incrementally verifiable proofs. So in this IVC setting, you have a continuous chain of computations, and you want to generate proofs for each of the steps of computations. What's happening now is that many of these IVC schemes are actually deployed in applications. So for example, I think the MENA blockchain, what they do is they exactly instantiate this IVC framework so that each of the steps is a state of the blockchain. And then you do continual updates with proofs. Well, they're deployed nowadays, but there is no sort of proof written down anywhere that these IVC proofs, they are resistant to malleability attacks. I'm also not saying here that this is a bad thing. I did not look into the whole protocol in enough detail to see if malleability attacks against these proofs will be a problem for the entire protocol or not. It's interesting in this setting is that now there are some sort of unavoidable attacks, you may call it attacks that may happen, right? So what you can do is you may get some proof somewhere that is valid, and then you can just continue the chain of computations, right? So already there is some modification of the definition that is necessary in order to preserve what is the intuitive security notion. And also, another thing that needs new technical ingredients is that these IVC schemes, they're usually built from a combination of 2 different primitives, right? You have both the non-interactive arguments, so this is back to the SNARK cases before, but they also combine it with an accumulation or a folding scheme. So those of you who saw Abraham's talk have heard all about folding schemes and how awesome they are. And these 2 primitives are combined together in an IVC scheme. And when they're combined together, what sort of extra things that you need to show in order to prove that the entire IVC construction is non-malleable? The second question is what I mentioned before, is that for non-zkSNARKs, you just want non-malleability, right? But somehow, in all of this talk, I just assume that the SNARK is already zk, and then I prove a stronger property called simulation-extractability. But we really just want non-malleability in some applications. Like some applications, such as these so-called zk rollups, they're not zk. They just want succinctness. So can we just directly prove non-malleability for such SNARKs? Like for Jolt, for instance. Can we show that Jolt is non-malleable? Here, I think maybe I haven't delved too much in this question, but at least on a surface level, it seems that you do need some new technical ideas, because these techniques for proving simulation extractability, it relies a lot on having a simulator. And so without a simulator, how do you set up the definitions? How do you make sure that the technical properties, they all go through, and so on and so forth?
So you're saying the proofs you showed so far would not go through if the simulator was not a simulator, but an oracle that I can just send X to and get back a proof.
Yeah.
Where would that fail intuitively? Like where would the proofs not go through?
So it's in. So if there's no simulator, right? So one potential definition is the adversary sends some proof. There's some like unbounded simulator that tries to figure out if there's a witness. If there is, then it generates a proof, right? What goes wrong in that definition is that now when you try to reduce to knowledge soundness, the knowledge soundness adversary cannot emulate this unbounded simulator. Just one particular way that does not go through. There may be other ways. So in this talk, I hope I have convinced you that simulation extractability and UC security are very important notion for SNARKs. It rules out these malleability attacks, which can be very devastating in practice. And it also, for UC specifically, it also guarantees security when you compose the SNARK with arbitrary protocols. So you really get like peace of mind when you deploy these SNARKs. And in terms of future directions, I've shown you sort of two open questions there. So if you're interested, please talk to me. I also like to work on these questions. And a somewhat further target might be, how do you formally verify these SIMX or UC security proofs, and how much overhead does that add to, say, the existing formal verification efforts that are ongoing?
Wasn't there a result that showed that NOVA, the IVC scheme, is malleable until you apply like a final SNARK at the very end of the IVC?
Yeah.
So can you hope to show then that these IVC schemes are simulation extractable or UC secure?
Right. I mean, it's probably going to come down to like IVC with these properties will satisfy SIMX. And maybe NOVA or whatever NOVA version that was do not satisfy that notion.
Do you have a sense of like if it's hopeless or not to have UC security if you only have rewinding extraction? Or like, are there examples of like, let's say you have a SNARK that was rewindable, like you get extraction through rewinding, but someone else later showed it was UC secure, like kind of separately?
I don't know of any UC result where extraction is rewinding. So it seems like still an open question to me. Yeah. What you can do is like, maybe you have some components that must use rewinding, but then you like add in some extra small components that are straight line extractable or something. Yeah. But still, you need straight line extraction somewhere. And I haven't seen that barrier being broken yet. Yeah.